Hi everyone, this is a video about extreme values in the closed interval test. We're going to start by defining extreme values. Extreme values are basically maximum and minimum values. Like we say extreme weather for weather that's out of the normal, it's a maximum or the minimum. So in the case of extreme values, we have something called a local maximum and something called a local minimum. So let's talk about that. F of c is going to be called a local minimum. It's a y value, f of c. It's a local minimum value of f if f of c is less than or equal to f of x for every x in I. So I means an interval around c. So in this picture here, for example, c is an x value, I is this little interval around c, and f of c, which is the y value, becomes a local minimum if we can say that that y value is less than the y values in a small neighborhood in a small interval around c. So that's a local minimum. Let's label it as such. This right here is a local minimum. Oh, can't seem to find the right color. Local minimum. And similarly, we can talk about a local maximum. That would be here at D. D is an x value. I is a little interval around that x value. And if I can go up to f of d, which is this y value, and say that it's higher, greater than the surrounding y values in this little interval, then f of d becomes a local maximum. Okay, and we can say that with math like this: if f of c is the local maximum value of f, if f of c is greater than or equal to f of x for every x in I. So in this picture, since we called this f of c over here in blue a local minimum, we used, d for this x value, right? But the point is, any place where you can make this kind of statement becomes a local maximum or a local minimum. So let's just look at this picture and finish off the other ones. Here, at this point, E, this right here would be a local minimum. Basically, it means the tops of the hills and the bottoms of the valleys, okay? And the hills and valleys can be sharp like this. It's fine. You can be differentiable or not differentiable. It's still a local extremum. So local minimum here, we'd have another local maximum here, okay? Now, something to remember is that the end values here, we're going to talk about them a little later, but these end values, I'll put them in black, right? These values cannot be local extrema because there's, if you go to this ending value here, let's call this x value, f, right? Then we cannot build a little interval here around f where this y value is greater than all the y values in the interval, for the simple reason we don't know what is to the right of f. We know what's to the left of f, and that endpoint value, y value, looks higher than the ones to the left, but we don't know what's on the right. So basically, an endpoint cannot be a local extremum. Okay. Let's go on to Fermat's theorem. Fermat's theorem says that if f of x has a local maximum or a local minimum at x is equal to c in an open interval, then either f prime of c is equal to 0 or f prime of c does not exist. So basically, we're saying that at any of these local maxima or minima, like we have these red and blue points in this picture, at all of those places, either f prime, which is the derivative, right, either the slope of the derivative is 0, like here and here and here, or the slope of the derivative is a DNE, which we can see like here. This would be a sharp corner, right? So f prime of this particular x value here, which is being called c, would be a DNE. So you can already see it in this picture. And this is Fermat's theorem. Fermat's theorem says that if you have a local maximum or a local minimum, then the derivative at that specific x value is either 0 or does not exist. So critical points are then going to be these numbers, these x values c in the domain of a function where f prime of c is either 0 or it does not exist. These are going to be called critical points. Critical points are sometimes called critical values or critical numbers. It means the same thing. It's places where f prime of c is 0 or f prime of c does not exist. So one of the key skills in this lesson is to be able to find a critical number. So let's practice doing that. Let me just preface this by saying this is going to be a case where every problem is going to be different because we're going to start with different kinds of equations. We're going to start with polynomials, rational functions, trig functions, exponential functions, all different kinds of functions. And so depending on the function, the algebra is going to be different. So I'm going to try to give you some examples here, but just keep that in mind that every time you do a problem here, you're going to be pulling from different pre-calc lessons about all these different types of functions that we know about. So let's start with a polynomial function here, and we're finding critical numbers, right? So to find critical numbers, you find the derivative. So for a polynomial, that's fairly easy, just with the power rule. In this case, 4x cubed minus 12x squared minus 4x plus 12. This is the derivative. And now we're going to set this derivative equal to 0. We want to find critical numbers. Let me remind you that critical points are those places where f prime of x is equal to 0 or f prime of x is equal to a dne. This is a polynomial for f prime of x, so there are no places where f prime of x is a dne. So I just have to find the places where f prime of x is equal to 0. So I will set my equation, f prime equation, to 0. And now you're going to use whatever techniques you have to solve equations. In the case of an equation like this, a polynomial, it's a cubic polynomial. My first strategy is going to be to try to factor. There are 4 terms, so I will try and see if factoring by grouping works, and I believe that in this case it actually does. And what do I mean by factoring works? Well, by grouping, that means if you try to pull out a common factor, you get this same thing in these 2 parentheses, right? Which means that the whole polynomial can be factored into x minus 3 times 4x squared minus 4. And then you can also factor this guy, 4x squared minus 4. You can pull the 4 out, and then the x, it would be x squared minus 1. And then you can further factor the x squared minus 1 into x minus 1 times x plus 1. And this whole thing has to be equal to 0. So you can solve this equation simply by factoring. So that's one way, certainly, that you're going to be using when you solve the f prime equals 0 equation. So in this case, these 3 values are the critical numbers. Now, notice that all these 3 are in the domain, all in domain of f. Critical numbers, remember, have to be in the domain of the function. In this case, the function is a polynomial. Every number is in the domain of the polynomial, so all these are critical points. Okay, let's do another one where we're starting with a rational function. F of x is equal to 2x minus 3 divided by x squared minus 1. Already you can see that to find the derivative, I'm going to have to do something quite different. I'm going to be using the quotient rule. So it's going to be low d high minus high d low over low squared. That's x squared minus 1, the quantity squared. Okay, and so we're going to simplify the numerator. Be careful here to first multiply these 2 terms right here. Multiply these 2 before applying the subtraction. And make sure that you keep writing the denominator as you go along. Okay, so I'm going to get 2x squared minus 4x squared, so negative 2x squared, and then plus 6x minus 2 on top, and then x squared minus 1, the quantity squared, on the bottom. Okay, so this is my derivative. Remember, For a problem like this, you know the goal is to set f prime equal to 0 and solve, and also to think about where f prime does not exist, because that's what, let me remind you again, critical points mean that. They mean f prime equals d and e, or f prime equals 0. Okay, so first of all, let me remind you that in this original function, x is equal to 1 and x is equal to -1 are the excluded values, right? It's a rational function, so x is equal to 1 and -1 are excluded from the domain of the function, okay? So if I end up with critical numbers being those two numbers, they are not really critical numbers because they're not in the domain. So let's take a look now at this f prime. If you look at the f prime, you can see that just like the function itself, this guy also has x equals plus and -1 as places where f prime is a d and e. So if I were thinking of this, I would go x equals 1 and x equals -1 because those two numbers make the denominator of f prime 0. However, these are not critical numbers or critical points because they're not in domain of f, okay? So that's all we have to do with the d and e. We have to think through that, f prime equals d and e. There are two numbers, those are not in the domain of f, so no critical points from that. And then f prime equals 0, we just take this f prime equation and think about what happens when we set it equal to 0. You know from before that if you cross multiply this function to solve it, then you just have to basically set the numerator to 0 and try to solve that equation. So I'll just multiply everything by -1 and divide everything by 2. Dividing by 2 means this guy will become -3x plus 1, right? And now I cannot factor, and so I'll use the quadratic formula. So x equals -b plus or minus square root of b squared minus 4ac all over 2. So I get 3 plus or minus the square root of 5 over 2. And these are irrational numbers that are in the domain of f. So these are critical, the two critical numbers, critical points or critical numbers, these two x values. Okay, let's do another example. F of x equals x to the -2 ln x. Find the critical numbers. So we take the function. X to the -2 ln x is, yeah, we can just work with it like that. If you wanted to, you could also work with it like this and write it as a quotient rule. Actually, I might do that. Let's do that. So then f prime of x is low d high minus high d low over low squared, right? Let me just show you here. Low is x squared, d low is 2x, high is ln x, d high is 1 over x. So low d high, that would be, let's color code, low d high minus high d low over low squared, okay? So then I can simplify. I know I'm going to be setting it to 0, so I want to simplify it and think of it as this is x minus 2x ln x all over x to the 4th, okay? So f prime equals d and e, let's think about that. That's one type of critical point. That will be when x to the 4th is equal to 0. With a rational function, which means a fraction function like this, when the denominator equals 0, then the whole function does not exist, right? Those are the excluded values. Well, so x equals 0 is the place where that happens. However, the original function that we started with up here, let me just box this original function. This also has a domain of x not equal to 0, right? So 0 is not in the domain of the original function, so this is not a critical point. Not a critical point because not in domain of f. Okay, so moving on then to f prime equals 0. F prime equals 0, take that whole equation that we found, x minus 2x ln x, which is the f prime equation, over x to the 4th, set it equal to 0. It's a rational equation. That's again like setting the numerator to 0. Now we have to think. We got to use all of our pre-calc skills, and this is why calculus is difficult, is because you are expected to know how to solve every type of equation from everything you learned in algebra and pre-calc. This one, I'd say we factor out an x, and then I'd have 1 minus 2 ln x is equal to 0. So again, by factoring, we can solve this because now we have two factors which when multiplied equals 0. So either x equals 0 or 1 minus 2 ln x equals 0. So then negative 2 ln x is equal to negative 1. Ln x is equal to 1/2. So exponentiate both sides and we get x is equal to e to the 1/2. So these now, I'll write them off here in red. X is equal to 0 and x is equal to e to the 1/2 or the square root of e. These are my two critical points for this function that we started with, right? So what does that mean again, these critical points? It means that these are the places where I might have a local max or a local min, right? So, I mean, this is actually pretty powerful, right, guys? We've taken a function that we knew nothing about right here, and we've boiled it down to, without graphing it, we've come up with just two possible places where we might have a local maximum or a local minimum. And remember, there's an infinite number of points on this function, right? Except for x is equal to 0, which is not in the domain. Literally every other x value is on this graph. However, without even graphing it, using calculus, we now know that the only two places where we might have the top of a hill or a bottom of a valley are x is equal to 0 and x is equal to 1/2. I think that's pretty cool. Okay, so now that we know something about local maximum and minima, let's talk about absolute maxima and minima. All of this, by the way, guys, is interesting because in life, it's often very important to find the maximum and minimum of something. Whenever we model something using a math equation, we're going to be interested in, how do we maximize, say, our profit? If you modeled your profit of your company with a math equation, you would want to know, how can I maximize that? If you're modeling your cost, you would want to know, how can I minimize that, right? So extreme values are very important in math and science, and that's why calculus is so useful in math and science. One of the reasons. Okay, anyway, coming to absolute extrema, let's talk about that. That means what is the highest hill or the lowest valley, right? It's about the highest point in the entire domain of the function, not just in the neighborhood or the interval close to a particular x value. So here we have the math definition. F of c is the absolute maximum value of f if f of c is greater than or equal to f of x for every x in the domain of f, right? We're talking Mount Everest. You are on the top of Mount Everest, then you are at the absolute maximum of the whole, f of the, land on earth, right? You are at the highest point. If you're just on a hill near your house, then you're at a local maximum. F of c is the absolute minimum, right? This will be, I think, maybe the bottom of Death Valley or something like that. I'm not really sure what the lowest point on Earth is, but the absolute minimum means you are at the lowest point. F of c is less than or equal to f of x, not just for the x's near c, but for every x in the whole domain of the function, right? So absolute is about the highest and the lowest. Just so you don't get confused, sometimes books and questions might call this a global maximum. And the other synonyms, the synonyms for local, right? We've said local, but there are synonyms for the local maximum are relative maximum or relative minimum, right? Because those are just highest and lowest relative to the neighborhood. Absolute means just globally, everywhere on the function, that's the highest or the lowest. So let's take a look at some situations that can happen with a function. So here's a function. So take a minute to pause the video and see if you can identify the absolute and local maxima and minima on this graph. Okay, so let me say I would immediately think this right here is a local max. Okay, this point right here, let's call it 3, 4. And in a question like this, you would just give a point and say 3, 4 is a local max. Right here, 4, 1 is a local min. Let's do the locals first. And then 6, 3 is another local max. What else? What else? This guy, surprisingly, which is 2, 2, 2, 2, is also a local min because it is actually lower than the surrounding y values here. So that's a local min. We said that endpoints cannot be local maxima or minima. They can, however, be absolute maxima and minima. So let me think about these endpoints here. This guy right here is not the lowest. Let's think about the endpoints and the absolute maximum minimum, right? So this right here is not local, that's for sure, because it's an endpoint, right? However, let's check, is it the lowest y value on the whole graph? No, it's not. The lowest y value is right here. So this point at 4, 1 will be the absolute minimum. It's already a local minimum, but it's also the absolute minimum. Let's think about the absolute maximum on this graph. Now, this is an interesting one because this hill right here is not the absolute max, right? Because all these y values over here, all these guys are higher, right, than that. So it's not the highest point in the domain of the function. The domain of this function, by the way, looks like it's just this domain, I would say, is 0 to 6. That's the domain, right? It looks like. Someone might quibble with my brackets and parentheses. I guess it would be bracket on 6 and parentheses on 0, right? That's the domain. But on this domain, this point right here, this right here is not the highest point on highest y value on the domain. All these ones are higher, right? But can we actually identify a highest y value? The answer is actually no, because these y values here are getting higher and higher and higher, and they keep on getting closer and closer to 5. But as you know from our lesson on limits, there's an infinite number of values here between 4.9, say, and 5, right? There's just numbers go on forever is the bottom line. So you can just keep on adding 9s as you get closer and closer to 5. So whatever number you might say, if you said this is the absolute maximum, then I'd say, no, it's this one. And then somebody else will say, no, it's this one. And then someone else might add another 9 and say it's that one. The point is there's no absolute maximum on this graph. And that will always happen when the endpoints are the highest, but there's an open circle on there, okay? If that had been a closed circle, if we had had a closed circle like that, then that would be the absolute maximum. Okay, let's talk now about the extreme value theorem. The extreme value theorem says that if f of x is continuous, we love continuous functions in calc, and it's on a closed interval, that means it's like, it's got closed circles on the two ends of its domain, right? That's what we mean by the closed interval AB, right? If f of x is continuous on a closed interval, then we can say that it will have at least one absolute maximum and at least one absolute minimum in AB, right? And you can kind of go off and think about whether that makes sense. If you are on some interval and the ends have to be dots and you're continuous, right? Whatever you draw in here, there's no way to not have a highest and a lowest point. Someone always asks me this question about what if it's like this, right? What if it's just a flat line? Then we don't have a highest and a lowest point. That's true. But in this case, honestly, every point here, say this is at y is equal to 10, then the absolute max of this function would be y is equal to 10, right? And in terms of a point, every single point on this line would be an absolute maximum. So you can have more than one point that classifies as an absolute maximum. But there is at least one point on every continuous function on a closed interval that is an absolute max or an absolute min. So that becomes then a way for us to use something called the closed interval method or the candidates method for finding the absolute extrema, maximum or minimum of f on a closed interval AB. And the recipe for that is it's kind of like in an election, you have to first identify the candidates, like who's in the running. The people that are in the running for the absolute extrema are the critical numbers, critical x values, critical points, and the endpoints, right? So we first find the critical numbers or critical x values. Then we find the y values, right, at those critical numbers. Then we find the y values at the endpoints, because when we're thinking about absolute maxima or local maxima, what is counting is, the y value. We might list the x value, but what we're comparing is y values. So we find the y values at the critical numbers and the endpoints. We make a table of those, and then we identify the highest and the lowest, right? So let's see how that works in a problem. So here, this problem says, find the absolute maximum and minimum values of f of x equals x cubed minus 3x squared plus 1 on this interval, right? So we're being given a domain for this particular function. We're noticing it's a closed interval, right? So we know from the extreme value theorem that there will be an absolute maximum and there will be an absolute minimum. So we go ahead and we follow our little recipe, which is step 1 is find the critical points. So we've got the derivative will be 3x squared minus 6x. So we'll just write that down here. F prime is equal to 3x squared minus 6x. There's nowhere where f prime equals dne because it's just a polynomial function. There's no holes or asymptotes or breaks or anything excluded from the domain. F prime equals 0, well, we'll set this guy to 0 and see what that gives us. Try to solve that. We can factor out a 3x, and then we can find that this gives us two places that are critical points, x equals 0 and x equals 2. So that's step 1. Step 2 is we're going to find the end. We're going to think about the endpoints, right? So in this case, the endpoints are -1/2 and 4. Those are the endpoints of the intervals. Step 3, I'd say, is to make the ballot. This is our candidates table, as we call it. On the left side are going to be the x values, which are the critical points, and endpoints, which are, so we list them in order. So I'll go with -1/2, and then 0, and then 2 and 4. Right? These are the only places where I might have an absolute minimum and an absolute maximum. The critical points are the only places where I might have a local minimum and a local maximum. But as you know, a local minimum or maximum might be also the absolute, so we have to list them. And then the endpoints might be the absolute maximum or minimum, so we have to list them. So we list all those, and then here we write the y values of these, right? So you have to go back into the function and plug in -1/2. So, and you might have a no calculator problem like this. So let's just practice doing this. So this will be -1/8 plus, no, minus 3/4 and plus 1. And so we'd put it all over a denominator of 8, and I think we'd get -1 minus 6 plus 8, or 1/8, right, is my number here. Then I'd put in 0, and I'd get out 1. Remember, it's going into f because I'm talking about the maximum and minimum on f. So those are the y values that we need. And then f of 2 would be 8 minus 12 plus 1, left to right, -4 plus 1, -3. And then for f of 4, I'd have 64 minus, let's see, 48 plus 1, that's going to be 16, I think, plus 1, or 17, okay? So that's it. I now have my candidates. These are the folks that are in the running. These y values right here are in the running for highest and lowest. So it's clear now that this right here is my absolute minimum on this domain for this function, and this right here is my absolute maximum on this domain for this function, right? So this takes me actually to something I want to mention on the next slide. This question was worded here. This question that we just did was worded, find the absolute maximum and minimum values, right? So really these numbers, f of, these numbers, -3 and 17, are the numbers we need. I usually play it safe by saying something like, I would end my problem with f of x has an absolute maximum at, I just put the point, 417, and an absolute minimum at 2, -3. So while we want to be aware that the questions, can be worded differently, it's always safe to give both the x and the y values. Okay, so that's our example there. Okay, let's do a trig function. It says find the absolute, example 6, find the absolute maximum and minimum values of the function x minus 2 sine x on the interval. Again, notice a closed interval, 0 to 2 pi, right? So x minus 2 sine x is our function. Let's just rewrite it here. Okay, so step 1 is find the critical points. F prime is equal to 1 minus 2 cosine x. Set that equal to 0. And notice, different equation, trig equation. We know how to solve those. And there's going to be different types of trig equations, and you have to know how to solve those. Okay, so cosine x equals 1/2, and we are on the interval from 0 to 2 pi, so x can be either pi over 3 or 5 pi over 3. Okay, so we take those two x values, and those are going to be in our candidates table, and then we think about our endpoints. I don't have to really rewrite it, but I'm just going to notice step 2 is identify the endpoints, okay? Okay, then step 3 we said is make a candidates table. So step 3 is going to be make the table, and in that put these x values. So I'm going to go in order, 0 pi over 3, 5 pi over 3, and 2 pi. Then I put the y values of those in. I go back to my function, which is x minus 2 sine x. So x minus 2 sine x is equal to 0. X minus 2 sine x is equal to, let's see, pi over 3 minus 2 times rad 3 over 2. So this is just going to be pi over 3 minus rad 3. Then I'm going to get 5 pi over 3 minus 2 sine 5 pi over 3. That now is going to be pi over 3 minus 2 times negative rad 3 over 2. So it'll be pi over 3 plus rad 3. And then 2 pi minus 2 sine 2 pi, which will be just 2 pi, okay? So guys, you are going to have to sometimes compare these y values without a calculator. So for a case like that, you want to just think about pi. Pi is roughly 3, right? So first just start with roughly 3 and see what you get, right? And then if two of the values are so close that you need to be more precise and go with 3.14, you can do that. But here we're comparing 0 and then roughly 3 divided by 3, which is 1 minus rad 3. Rad 3 is greater than 1, right? So this is clearly a number less than 0. Here we have 1 plus rad 3, right? And then the last one we have is 2 times 3, or 6. So clearly this guy is going to be my absolute maximum because it's close to 6. Rad 3 right here has to be between 1 and 2, so it's not going to get you up to 6. So this is my absolute maximum, and my absolute minimum will be this negative number because no other number is negative, right? So this is just an approximation, right? I did that just because to show you if you don't have a calculator, that's how you think about it. But you'd finish your problem by saying f has an absolute max, and you want to use then the exact values. So you would say f has an absolute max at 5 pi over 3, comma, and then you give the whole y value like this, right? and an absolute min at the other one, pi over 3, comma, pi over 3 minus rad 3. Okay, the last example I want to show you is a word problem and one that would involve your calculator. It says, the Hubble Space Telescope was deployed on April 24th, 1990 by the Space Shuttle Discovery. A model for the velocity of the shuttle during this mission from liftoff at time t equals 0 until the solid rocket boosters were jettisoned at t is equal to 126 seconds is given by v of t is this function right here. You're seeing all these decimals, right? So right away you know this is a calculator problem. And the velocity is in feet per second. Estimate the absolute max and min of values of the acceleration of the shuttle between liftoff and the jettisoning of the boosters. So jettison basically means, you know, when the boosters come off and they get kind of thrown off. That's what they're talking about here. So notice that they're talking about acceleration, right? So we want to first write our velocity function, which is what they've given us. I'll just rewrite that function. It's 0. Oh, I think I have a little typo here. I'm going to flip these two numbers. So it's 0.001302 t cubed minus 0.9029 t squared, right? So you'd be putting this into your calculator maybe, or maybe not. Let's see what we want to do with it. Okay, so this is the velocity, okay? We're looking to maximize the acceleration. So the first thing will be to get a function for the acceleration. And for that, you know, we just do the power rule. And so it'll be 3 times this decimal, which you can do in your calculator, or you don't really need your calculator for that part. And we're going to get, I think I dropped a 0 here. Okay, so we're going to get something like 0.18058 t plus 23.61, right? So first thing will be to find the function that we're trying to maximize, which is the acceleration. And now we go to our way to find the absolute maximum, right? We know that we're on this interval from 0 to 126, right? And we want to include 0 and 126. It's a closed interval, so we can just apply the candidates test. So I know already my endpoints. Those are going to be 0 and 126, and I just have to do my critical points. So I'll now find the jerk. Oh, I've been waiting for a problem on which I can take the derivative of the acceleration, and here it is. And let's see, it's going to be, you do 2 times this number, right, which comes out to be 0.07812 t minus 0.18058. It's just a simple power rule problem, but it's just using decimals, right? So here's my a prime. And remember that for a critical point, a prime has to be equal to dne or 0. There's no dne's on this guy, so it's just going to be setting this thing equal to 0 and solving. And you're going to find a time. It's just a little linear equation, so you just solve it. I think I might have made... no, I didn't make a mistake. Good. So it's 18058 divided by, and you can like follow along with all this in your calculator and check my math. Hope I didn't make any mistakes. I don't think I did. This one is t is equal to 23.116 seconds. So that's a critical point, and that goes in our table. That's a candidate for an absolute maximum. Okay, so we've got all our candidates, the endpoints and the critical points, and now the thing that we're trying to maximize, and this is something to be careful about, this is what we're trying to maximize, right? So that's what goes in the y column here. So a of 0, that comes out to be 23.16. I seem to have a problem flipping decimals. It's 23.61, I'm sorry. And then we have the this 23.116, you would go put it back into the A of t equation, into this yellow equation, and you'd get a number out, 21.523 for the acceleration, and then you would put the 126 time into that equation again. All these go into that yellow equation to get our y values, and you get 62.869, right? So we can see that our maximum acceleration is here at this time, and our minimum, this is the absolute maximum on that 0 to 126 seconds, and this is our absolute, not that one, I'm sorry, this right here, this at t is equal to 23.116, we hit our absolute minimum, okay? So this would be one where we want to read the words, and it says estimate the absolute maximum and minimum values of the acceleration, right? So here we're talking about the y values. So we would give an answer, absolute maximum acceleration on this interval, right, is, and you just have to give the y value, is 62.869, and this will be in feet per second squared. And then absolute minimum acceleration on this interval is the other number, 21.523 feet per second squared. Questions can be listed differently. Sometimes they say find the maximum or minimum of f. In that case, we are going to provide just the y values. Sometimes the question might say at which x does the function have a maximum or minimum, then we need to provide the x values. And if the question just says at which point does the function have a maximum or minimum, then we need to provide both the x and the y values. So let's see how. Okay, so let's take a minute, pause the video and see if you can do the takeaways. And the takeaways are that extrema means basically maxima or minima. That's the plural of maximum and minimum, right? Extrema means the highest and the lowest y values. Extrema can be absolute or local, and absolute can be called global, and local can be called relative. If a function has a local extreme value at x is equal to c, then f prime of c must be 0 or it must not exist. This is Fermat's theorem. Critical points or numbers are x values where f prime of c equals 0 or f prime of c does not exist, right? And the c's, these x values, are the critical numbers, right? Extreme value theorem says that a continuous function on a closed interval, AB has or will have at least one absolute maximum and at least one absolute minimum on that interval. And lastly, candidates for the absolute maximum and minimum are the y values of the critical points and the endpoints of the function on AB, right? And remember, endpoints means f of the two endpoints, the y values of the two endpoints. Okay, hope you enjoyed that, and yeah, make sure you do your homework, which is a lot about the vocab as well as finding critical points.